All right, so let's go ahead and I'd like you to advance the slide, facilitate if you would to this point right here. And let's take a look at this one, because this one is probably one of the more difficult pictures for us to try to understand. Let's go ahead and see that this is actually a three-dimensional globe shown on a two-dimensional surface, so it's pretty hard to understand or visualize. If you already did this exercise, that's fantastic, because not necessarily everybody has it before the first night of class. Why? Maybe they didn't receive the goodie bag or box, or you didn't get a chance to work on it. So we're not going to panic about it. It still needs to be done. But if you have that finished, you should bring it out here and take a quick look at it, because this really is essentially the same thing as we have up here. The north, and you can't tell from my globe here, I'm too far away from the camera, but the north is facing the north here, and obviously this hemisphere, half the sphere, is the top half of this thing. All right? So, if you've done yours correctly, you should have marked Polaris about 35, 36 degrees up from north, and that's what we put in here. This is Polaris, and this is about 35.5 in Oklahoma City, maybe obviously greater. Tulsa is slightly north than Oklahoma City. So Tulsa would have a different value in here, but you can put 36 in there if you want to. That's perfectly fine with me. So there's Polaris, there's 36. Notice that 36 is the altitude of Polaris, and it is the same as the latitude on the Earth. So here's the Earth, swing it back around, there's the equator, and then, Oklahoma City, Polaris is up, Oklahoma City, and Tulsa is up here. So we're talking about 35, 36 degrees right there. The latitude is matching the altitude of Polaris. This is the altitude right here. So, for this person standing there, looking straight above, that would be his or her zenith. Straight down below would be the nadir. Now this north-south plane that you see right here, and this is marking this heavy line, on that side of the line is east, on this side of this heavy line is west. Just like if you take a look at your azimuth globe right here. So this is south, this is north. There's a line that marks that, like an indent in the plastic, and that is your meridian. There's also an indent over here, but when these hemispheres are made, they weren't necessarily made to mark out the meridian or anything else. It gives it a little bit more rigidity, if you will, a little bit more strength. But it just so happens that if you've lined it up correctly, then at least on this one large indentation, that would be the meridian, right? There would be the zenith at the top, the meridian would be at the bottom. So, this indentation we see is the exact same thing as the line that we have right here. So the north-south plane is the meridian, and Polaris should be right on the meridian. Polaris should be on the meridian. Okay, so we got everything up there except where it says, show the path of the stars that rises in the east and then transits and sets in the west. That's going to be a little bit harder to show. And it says down here, go ahead and trace it out for the southeast, east, and the north. If you haven't done that, you probably haven't, because this is kind of difficult to see. I'll try my best to show you with perhaps a laser pointer or with my finger. Let's answer number 6 right here. Star's going to rise here, and the most important thing is to see that it rises at an angle. It doesn't come up here in Oklahoma City or Tulsa. It doesn't come straight up and over the top. That's the most important thing to see. And you should get a chance to figure this out in Stellarium too when you apply some of those, or complete some of those exercises. The star rises east, and it rises at an angle here in Oklahoma City. In fact, that angle is at an angle of around 35, 36 degrees. So what it does, it comes here at an angle, still on the eastern side, and then it transits, and then it comes down here and sets in the west. Now, hopefully, if you have everything you need there in Tulsa. You also have something like this, which is really, I think, pretty cool. It's almost like a pincushion. But what this shows is the path of the stars, or star, or whatever it might be, that rises in the east. It transits and then sets in the west. So it's a little hard for you to see. I'm sure it is. A little hard for you to see. But there's east, there's north. So 1, 2, 3, 4, 5, 6. It actually takes 6 hours to transit, and 1, 2, 3, 4, 5, 6. 6 hours to set. So notice, if you will, when it's rising in the east, it's rising at an angle. It's not going straight up, it's actually rising at an angle, which is pretty cool to see. So I made this thing. It's not perfect by any stretch of the imagination, but it's at least allow you to see how stars will rise at an angle, they transit at the halfway point, and then they set. The same thing is true for a star that rises in the southeast. It rises at an angle. Again, difficult to see, but if your facility has this, you can actually pause the video now if you want to, and try to understand these a little bit. And you can count 1, 2, 3. 3 hours before it transits, it's risen so far south, doesn't get very high in the sky, 3 hours, and then another 3 hours before it sets. And the same thing's true with, let's say, the green line right here. It rises in the northeast, and 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 hours before it transits, 9 hours before noon, and then 9 hours to it sets. So 9 hours after transiting, and that's 18 hours in the sky. I'm going to show that to you up here in a second. And then you can see, for those stars that are very near to Polaris, there's Polaris, that they just go round and around, round and around, and that they actually never set, and they never rise. They're always going around, and they're up all day and all night. And that means that they're circumpolar stars, right? So that's at the end of the chapter, you should check that out. It's probably a little difficult for you to see this, so let's go ahead and look at the next slide. This is what you should really show. And maybe if you have your colored pens or use dotted lines and solid lines and things like that, you can show all these, okay? You should stop the video really, anytime of course that you want to, but I really recommend that you stop it and compare what you see here with what you see on this particular pin cushion of a hemisphere if you want. And before you do that, I would say that if you had a chance to get out a transparency pen and just bend up the part that that helps hold it down, like you've got in your pocket and so on, little clip. It looks something like this, right? This helps you see that if this is the axis of the Earth, as, of course, the Earth is spinning, but from our perspective, it looks like the sky is moving. It's no wonder that with that kind of angle, that this thing, this little piece right there, is going to actually mark out the path of that star. And it's going to do it. If this thing is like 90 degrees with the axis of the Earth right here, it's going to do it. It's going to make an angle. It's going to make an angle with respect to the sky right there. And again, before you go, you might take this and go ahead and hit that pen and bring it along in there and along the shaft or along the axis of the Earth. And you can see, it's going to be very difficult for you to see where you're at, but your facilitator can show you this. When you go ahead and rotate that pen, that this part actually points out where the star is going. And because Polaris, the axis of the Earth is tilted with respect to our horizon, tilted here, then it follows the pathway. You can do it for the yellow, you can move your pen down a little bit and do it for the blue. You can move your pen up a little bit and do it for the green. And you can see clearly why it's at an angle here in Oklahoma City. So go ahead and pause the video for a moment and work on that. All right, are you back then? Good, okay. Well, I hope you enjoyed trying to understand that at least. So let's take a look here. Where do you think this is located at? Where do you suggest this is located at? You can go ahead and pause if you want to and talk about it as a class. I suggest you do that unless you think you know the answer. Go ahead and pause it real quick. If you ask me, this is then located at the, what would it be? It would be at the equator, right? It would be at the equator. Why? Because believe it or not, Polaris is right there to the north. And just think about this pen. You go, if you've got the pen like this, the pen, the axis of the Earth is pointed towards Polaris. If it's at the equator, the pen, you look north, and there's Polaris right there on the northern horizon. 0 degrees latitude, therefore Polaris is 0 degrees altitude. You're right there, and you go like that. Here you go like this if you want to. And you can see that at the equator, the stars rise vertically out of the horizon, and they set vertically into the horizon. That's very, very different from the slide before for Oklahoma City or for Tulsa. Okay? Here is at the equator. All right? Again, pause it because I'm going to show you another slide if you need to, if you need more time to understand this. Okay, so where would this be at? all the stars are going around and around and around and around, and none of them are rising, none of them are setting. Of course, they're all going around the pole star, so Polaris is at the top. If Polaris is at the top, at a zenith of around 90, then we're obviously at the North Pole. Because Polaris is at the top, it has an altitude of 90, which matches the latitude on the Earth. So you're clearly at the top of the Earth right here. You're at the top of the Earth looking straight out, and all the stars are just going round and around, round and around. None of them are rising, and none of them are setting. If you want to, you should really go to, and I can do this for you, you go to Stellarium and show all this. It's quite easy to show, all right? I think, let's see here. Let me get out of here real quick, and we'll get into Stellarium. A little bit hard to see with the light here, so I'm going to turn the light off, but then it gets so dark. Maybe I have to see if I can get another light in the background to kind of help see some things. All right, so we're actually, according to this, we're actually in Paris, which is kind of weird. So I don't know why we're located in Paris, so let's go ahead. And we're just going to go to a latitude of 0. So we're going down to the equator. And I'll go to 0 here as well. And let's see here. My latitude is 0, 0, and 12. All right. So I adjust. I'm somewhere down here in the middle of the ocean. You can see the red marker right there, but the equator is going across the Earth. So it's fine, no big deal. So I'm going to look over here to the east, and put the east up there. So that's the horizon's flat. Show you some constellations. All right. So now let's go ahead, and I'm at the equator. Let's go ahead and watch. What are the constellations doing? You can see that they are rising straight up. I'll go ahead and turn off the atmosphere so it doesn't become day. But they are rising straight up. Look at that. That is at the equator. Just like that picture I showed you a moment ago. Let's go ahead and I'll stop the time. And we'll adjust our location. Probably not, Stellarium doesn't actually like you to be exactly at the equator. So I'm going to adjust it to, say, 89. We're up there, maybe 89 degrees, and maybe, 56 minutes, something like that. So, I think I've got this right. I can't even see, unfortunately, I can't even see the red arrow any longer. But I do believe I'm at the North Pole, okay? I hope I am. Let's see. We'll find out here in a second, because look at the path of the constellations at the North Pole. None of them rising, none of them are setting. They're all going to Polaris. Of course, Polaris is the pole star here. There's Polaris right there. Straight up above you at the zenith. And in a sense, if I back out far enough and look at the whole sky, they're all turning counterclockwise about Polaris. And none of them are rising or setting. They're just simply skimming the horizon, which is super cool, right? Because you can see that's exactly what I've shown you right here. Right here. Very, very cool. All right. You guys can use this if you want to. I'll turn on the lights so you see this a little bit better. But go ahead and answer this question. What can be said of the altitude of Polaris at Dallas compared to the altitude of Polaris at SMU? This would be a great quiz question for you. Maybe coming up next week. Have you had a chance to think about it? Well, Dallas is south of us. Dallas is south, and therefore Polaris is going to be lower on the horizon. It's not going to have as great of an altitude. So the answer should be B as in boy. Polaris is at a lower altitude in Dallas. That's pretty straightforward, I think. Again, if you look at your star trails in your workbook drawing, I showed them a couple slides ago. Let me go back here so you can see them. All right, those are the star trails from Tulsa or Oklahoma City. A star rises and transits 9 hours later. In what direction will it set? This is a tough question, but you should be able to get it. If it's spending so much time up in the sky, it's going to follow this green pathway here. It's going to follow the green pathway. It's rising in the northeast, coming up, transiting, and then setting in the northwest. The answer here is C, as in cat. If it were rising due east and setting due west, it would transit 6 hours. Just count the yellow here if you want to. 6 hours and 6 hours. Things that rise due east take 6 hours to transit and 6 hours to set, so 12 hours total. Things that rise in the southeast, that's the blue, southeast, they don't spend very much time in the sky here in Oklahoma City or Tulsa, and maybe 3 hours, and then another 3 hours to set, only 6 hours total in the sky. So this is a tough question. It really forces you to kind of understand and maybe visualize if possible. This would be one of the tougher questions you would face in a quiz, and thankfully there's not too many that are like that, but hopefully this makes sense in the context of what we've just talked about. And this picture here kind of elaborates it pretty nicely. How about this one? A star rising takes 6 hours to transit. In which direction did it rise? Again, east. All right? So, again, 6 hours to transit, 6 hours to set, 12 hours in the sky. The answer is B as in boy. Okay, well, here's the good news for those of you who are in this bridge astronomy course, that we're not going to spend a lot of time talking about the equatorial coordinate system. I asked you to read it, but we won't spend a lot of time on it. And the reason is because it really does take a lot of time. And that's frankly time that we don't have in this course. I do want to just clarify for you, though, that it's pretty important to recognize why we need some other coordinate system besides the alt-azimuth. And I'm going to need a facilitator's help on this. Because what I'd like you to do is, the facilitator, go ahead and choose something in the room. Something that is, I don't know, it's just some corner of the room or just something that is interesting, that's easy to look at. Maybe, in my case, you can't see it, but I see an emergency light there. There's a speaker over there. There's a corner of a chalkboard right there. Whatever, just choose some option for everybody to look at. Now, if your folks are spread out in the classroom, you can ask them to find the alt-azimuth. All right? So if it's something over there, I'm going to start north and then count fast to get to that. And then I want you to find the altitude of that object as well. So everybody individually in the class, and especially if they're spread out, go ahead and find the alt-azimuth of that object that you selected. And then compare the notes. What are you going to find? What you're going to find is that everybody has a different value if they're far away from each other. If they're all close and sitting in a clump, and they're all together like this, and they use their fist, they're probably going to get similar results. But if one's sitting in that chair over there, and one's sitting in that chair over there, and you try it, you're going to find that everybody has different values. So pause the video and try it now. Everybody get a chance to do it. Choose an object, find the alt-azimuth, every one of you individually. Alright, so what you're going to find out is that everybody came up with a different value, right? And this is akin to astronomers all over the world, maybe even in the United States, or maybe in the state of Oklahoma. Because just think about it. Maybe you're in Tulsa, and the sun has risen. It's rising on the horizon, so it's 0 degrees altitude. You call your friend in Oklahoma City, which is further west, and say, the sun at this present moment has an altitude of 0. It's right on the horizon. Well, in Oklahoma City, which is further west, it's still dark. The sun hasn't even risen yet. The sun is below the horizon in Oklahoma City. It has a negative altitude. So clearly, this is not a good way to communicate when your locations are far apart and you get the whole classroom thing, right? The same thing was true if you're spread out in the classroom. So the alt-azimuth breaks down anytime you're talking and communicating with people that are some distance away. You know, if everybody's out in the backyard or maybe within the same city, it's probably close enough in proximity for you to compare notes with your alt-azimuth. But anytime you're stretching out distances, you're going to have to use something else that's more universal. And that's where the equatorial coordinate system comes in. Again, we won't spend a lot of time on it. I do want you to appreciate that really, just like the Earth has latitude and longitude, the equatorial coordinate system also has lines of what we call right ascension and declination. I'll just show it real quickly with the globe that's right here. And let's see, I guess I'll hold maybe the globe like this. And these are lines of latitude on the Earth. So out here in this celestial globe, you also have lines of declination. And just like the Earth has an equator, out here on the globe, it also has a celestial equator as well. And you have these meridian lines on the Earth, and that's what I'm showing you right here. This red dominant line that you see right here is the prime meridian. It goes right through Greenwich, England. There's the prime meridian right there. And you extend that out into space, and wherever England is out here, there's the United States, so England is right there. And there's the prime meridian out here, and then you've got these, well, that's the right ascension right there, and then you've got these hours of right ascension. That's when it starts getting real confusing. Here I am standing at the prime meridian, and just like we have on the Earth, the prime meridian, out there on the celestial globe, you also have right ascension lines. Now, it's a little bit hard for you to see. You can watch various videos if you want to. You'll see something like this, and it's completely up to you if you want to watch it. It just depends on how much you are in astronomy. We're not going to have very much, if any at all, except an appreciation of the equatorial coordinate system with right ascension and declination. So obviously you don't have one of these beautiful globes. They're worth about $400. You don't have one there in Tulsa, so you're at a little bit of a disadvantage. And all I want to say is that just like the Earth has a coordinate system, so does the celestial globe, so does the celestial coordinate system, the equatorial coordinate system. And just like the Earth has an equator, this also has a celestial equator. And the stars are glued onto this globe, and they all have right ascension and declination. So that's a much more straightforward way of talking and communicating with people. If you have like an Astronomy Today or a Sky and Telescope, when they give you the location of various objects, they give you that location in right ascension declination. Why? Because it's going all over the world, right? Different people are reading it, and it's a more universal system for communicating the coordinates of these objects in the sky. So one thing that is very, very important is part of the celestial coordinate system, or the equatorial coordinate system, is what I referred to earlier as the ecliptic. You can see here, this is a really beautiful picture. Probably could have shown it earlier. When I was describing, you remember what the ecliptic is. Because there's the sun, there's the Earth going around the sun. So this grid pattern that you see here forms a plane that's called the ecliptic. And when you extend that on out, what do you hit? Well, you hit the zodiacs. There's Taurus, the Bull, Aldebaran, and there's Gemini, Pollux and Castor, and so on. Looks like there's Cancer, the Crab, there's Leo, the Lion, and Regulus. These guys are all on the ecliptic, as you can tell. So that's pretty cool. Again, this is actually kind of looking from behind the Earth, if you will. And from our perspective on the Earth, let's say the Earth is like right here, and I'm looking in this direction, kind of looking over the shoulder of the Earth. Here's the Earth, I'm looking over the shoulder of the Earth, and you can see that the sun, from my perspective on the Earth, looks like it's just this direction of Polaris. So there is the ecliptic right there, and the sun will move along the ecliptic this direction. Why? Because the Earth is going in this direction around the sun. So again, let's see. If I'm looking at it from about right here, I can see it about right there. Okay, and that's what you see right here. But going here, as I move along the ecliptic, move along the ecliptic here, now I see the sun. It's there. A little bit further, maybe at this point, the sun is right there for the Earth. And so again, down to this side, if you will, as the Earth is moving, it makes it look like the sun is actually moving along the ecliptic right here. So it takes the sun 1 year to move all the way through the zodiacs, because it actually takes the Earth 1 year to go around the sun. So there's the sun moving, maybe a month at a time, give or take, through these zodiacal constellations, and it takes 1 year to go through the zodiacs, right? If you think about it, I wonder what this object is. This is probably the moon, isn't it? It takes the moon 1 month to go around the Earth, and of course the Earth continues to move, but the moon still takes about a month to go around the Earth, and therefore the moon is going to move through the zodiacs, the entire zodiacs, in about 1 month. Exactly 29 and a half days, to be honest with you, or to be more precise with you. So the moon is also moving somewhat in the ecliptic, not perfectly, and it takes about a month to get around the Earth. Therefore, the moon is moving through the zodiacs along the ecliptic in about a month. So that's pretty cool. Well, I'm not going to draw it out here because there's just too much. We're going to move quickly through it, but here's the Earth's own latitude and longitude, and then for the celestial coordinate system, you've got right ascension measured in hours, you've got declination measured in degrees, very akin to what you see on the Earth. And what you see now is the ecliptic here versus the celestial equator. The celestial equator is an extension of the Earth's own equator, but the moon moves along this ecliptic. It's quite confusing, especially when you look at it two-dimensionally. But the reason that there's a difference, and I'm really not trying to belabor the point here, but it's worth you appreciating. This is something you won't have in Tulsa, unfortunately. It's something that I made to demonstrate what's going on here. And what you see here, let's see if I can get this to kind of line up a little bit with like what you see up there. This is three-dimensional. Guess what my little tennis ball represents? It represents the sun. So this blue here is the Earth's own equator extended out to this blue hula hoop. All right? But because the Earth is tilted, if the Earth were not tilted at all, the ecliptic would be lined up perfectly with the extension of the Earth's own equator. Well, I can just tell I better stop right now because I'm sure it's getting confusing, and you may be laughing at me at this point just because it's so ridiculously confusing. Well, I don't want to spend too much time on it, but I'll just say this, that if the Earth were not tilted at all, if the Earth were like this, as it went around the sun, this is what you'd have like this, okay? And the sun would be going along here, and you wouldn't have any seasons, you'd have relatively very light seasons, if you will. And if there were no tilt, you wouldn't have any seasons. But when you take the Earth and you tilt it like this, out of the ecliptic plane, then you do have seasons. Now this diagram here is did you notice I made a tilt, right? You saw that. You saw me go like this. I made the tilt. This is similar to that, except what? All I have to do is like fix it by keeping that same tilt and making it like this. The blue line represents that heavy solid line, the celestial equator, and now you see, day by day the sun is moving along the ecliptic, right? The previous slides where I showed you that grid, day by day, day by day, day by day, day by day. And it takes one full year to go all the way around the ecliptic. So the reason that there's a difference between this line of the ecliptic and the celestial equator is because the Earth is tilted 23.5 degrees. So this is a really nice three-dimensional kind of gizmo that demonstrates some of these things. But again, I don't want to spend too much time talking about it, all right? So again, I'll move past some of this stuff. All this is interesting. I could have taken it out of here. But suffice to say, this is where we're going to end up. If you need to rest your brain for a while, you should pause the video now because we're going to end up talking about circumpolar stars and just spend about maybe 5 minutes hopefully on that. Okay, so let's finish up here with circumpolar stars. I don't know, maybe your memory is, or your brain is a little tired, but you remember from some time ago I showed you a solarium and how all the stars are rotating about Polaris. That's what you see right here. Is all these guys are rotating about Polaris. So from that person's perspective, let's see, it should be going counterclockwise in the sky. So from that perspective, it's kind of going like this. A little hard to see with these arrows being three-dimensional, but that's what this particular diagram is showing. From that person's perspective, things are going counterclockwise like this. So if these stars are close enough to the axis, they will never set, and therefore they're circumpolar. I love this. I actually took this picture. It's not a great photograph, It's not the cleanest photograph in the world, but it's still pretty cool because these are star trails. And I assume I probably had my shutter open for, let's say, about an hour or so. And you've got these little dots and stuff like that. It's just really from the photosensor, the CCD chip, getting kind of hot and maybe, these are some of the mistakes that are in that long exposure. But these lines are because the Earth is spinning. Now, the one cool thing is, where is Polaris here? Polaris is not super bright, but it's one of the brightest stars shown here, and there's Polaris. It doesn't move very far. Obviously, things that are farther away from the axis of the Earth are going to have longer trails, and you can see that right there. But there's Polaris. The most interesting thing is that it's actually not exactly on the horizon, or right on the pole, excuse me. It's just slightly off. It's like at 89, it's like 89.5 degrees, declination, which we're trying to avoid. But the point I'm trying to make is that Polaris is not perfectly on our axis of the Earth. Well, that's not a big deal. It still really suffices as a great pole star. Here I've shown you kind of a blow up of the previous picture, taking a look at about that much space, and you can really see, again, it's just a little bit off from the axis. Well, if you want, you can pause this video.